Good morning. I welcome you all to this session of fluid mechanics. Today we will be starting a new chapter, Kinematics of Fluid. But before that, I like to deliver a closer talk of the earlier chapter which we discussed in 6 lectures, that is fluid statics. That I will just highlight the main points so that we can have a quick go through all the main points in the chapter fluid statics. So this is a closing the chapter. First we recognized that in that chapter in a fluid at rest there are 2 types of forces that act in a fluid body at rest. If we take a fluid body in isolation from its surrounding fluid, from a vast expanse of fluid, we recognize 2 types of forces acting. One is the body force, which is due to the external agency, just like the gravitational force. There may be different body forces. Another is surface force, which act at the surface of the fluid body in isolation because of the reaction or mutual interactions between this fluid body with its neighboring fluid particles from which it has been kept separate. Then we recognize that fluid at rest can neither develop tangential stress nor tensile stress. Only the stresses are compressive in nature. That means at a point the stresses are directed from all direction towards the point and they are of equal in magnitude. That is known as Pascal's law. Then what we found that in a fluid expanse at rest, expanse of fluid at rest, if we consider only gravity force is the external body force field, we see the pressure in any horizontal plane remains same. That pressure does not vary with any coordinate axis in the horizontal plane. It only varies in the vertical direction. And we have recognized the basic equation of fluid statics in that respect is dp dz, the differential of p with respect to z is equal to minus rho g, where rho is the density of the fluid. The minus term comes because if you take the z axis positive vertically upwards, alright, then we can solve the equation explicitly for p as a function of z provided we know the variation of rho with z or p. For an incompressible fluid it gives a simple solution, p is equal to rho g z, where z is the vertical height plus some constant which is found out from an arbitrary datum value. And from this we lead to a conclusion that the pressure at any point in a static expanse of fluid is over the atmospheric pressure, where there is a free surface and pressure is the atmospheric pressure, by an amount which is equal to rho g h, where h is the depth of the point from the free surface. Then we recognize pressures on submerged surfaces. Now if there is a plane surface submerged in an expanse of fluid, so the net hydrostatic pressure force is equal to, this is the formula we derived, equal to the pressure intensity at the centroid of area or the center of area of this surface times the total area of the surface. In general, area may be inclined, area may be vertical, area may be horizontal, the formula remains the same. And we also appreciated from common sense that obviously since the pressure increases with the depth from the free surface, center of pressure is below the center of area. That means the depth of the center of pressure from the free surface is more than the center of area. And the distance between the center of area and the center of pressure along the axis of symmetry that pass through the center of area is given by a term, that is moment of inertia of this plane area through a centroidal axis which is parallel to the line of intersection between the plane surface extended to the free surface. The moment of inertia about an axis parallel to this axis through centroid divided by the area itself times the coordinate or the distance of center of area from that reference line, that is the line of intersection between the plane surface and free surface. For a curved surface we recognize that each and every force on elemental surface are varying because they are normal to the surface, because of the curvature of the surface they are varying in directions. So in that case we found out the components in some reference directions and we had the conclusion that the component of hydrostatic pressure force on any curved surface in any horizontal direction equals to the hydrostatic force on a plane surface, which is the projection of the curved surface on a plane perpendicular to that directions, in which the component of the hydrostatic pressure force is short. And the vertical force acting on a curved surface equals in magnitude by the weight of the fluid vertically above the curved surface up to the free surface. That means the weight of the bulk of the fluid which is contained between in the region, if we vertically extend the surface up to the free surface by vertical projection, then the bulk of the liquid contained within that volume is the vertical force acting on the curved surface, vertical component of hydrostatic force acting on the curved surface. So this way we recognize the magnitudes of the three components or different component forces with respect to a frame of coordinate references, and finally we find out the resultant force. Then we came to the concept of buoyancy. As you know, when a body is partially or totally immersed in a fluid, the net effect of the pressure forces around its surface gives no resultant force in the horizontal direction. They balance each other. But this gives rise to a net force in the vertical direction which is acting vertically upwards, and that force is known as buoyant force, and this phenomenon is known as buoyancy. Now for a floating or a submerged body to be in equilibrium, the primary condition is that weight of the body which is acting downwards must be equal to the buoyant force, and these two forces must be collinear, then only it will be in equilibrium. Then we recognize three types of equilibrium. We have read in the preliminary mechanics. One is stable equilibrium, neutral equilibrium, and unstable equilibrium. For stable equilibrium, for submerged bodies, we have found that the gravity, center of gravity should be below the center of buoyancy. Whenever the center of gravity is below the center of buoyancy, always it is in stable equilibrium. But if center of gravity is above the center of buoyancy, it will not be in stable equilibrium, it will be in unstable equilibrium. And if they coincides, then the body will be neutral equilibrium. Well, but for floating bodies, the beauty is that when the body is given an angular tilt to check its stability so that it can come back or not to its original position, the center of buoyancy also changes, because some part of the body gets up from the free surface, some part gets down, is immersed. So therefore, even in this case the G is above B, there is a chance for the body to be in stable equilibrium, which is decided by another point known as metacenter. So if the metacenter is above the center of gravity, the definition of metacenter is the point of intersection between the vertical lines drawn to the new center of buoyancy to the old line, old vertical line containing the old center of buoyancy and the center of gravity. So this is the definition of metacenter, and when the metacenter is above the center of gravity, the floating body is in stable equilibrium. If metacenter is below the center of gravity, the floating body is unstable equilibrium, and metacenter coincides the center of gravity, the floating body is in neutral equilibrium. Alright, then we appreciated that for small angular tilt, this metacenter is a geometrical parameter of the floating bodies. It is a function of the geometrical shape and its dimensions. And we found out the distance between the center of buoyancy to the metacenter along the line of symmetry or the vertical line containing the center of gravity and old center of buoyancy under equilibrium condition, center of buoyancy under original equilibrium condition, can be found out if we designate this as B and M, and the distance as BM is equal to I by V. What are these nomenclatures? I is the second moment of area of the plane of flotation of the floating body. Second moment of area of the plane of flotation, that means the plane of flotation. If I see a section of the floating body at the plane of flotation, the second moment of area of this sectional area at the plane of flotation about the axis of rotation, that means about an axis perpendicular to the plane of flotation. So this is the nomenclature of I, and V is the immersed volume. So this we recognized in the last class, and this is all. So now I will start the fluid kinematics. Now what is kinematics of fluid or fluid kinematics? Now kinematics of fluid describes the fluid motions, basically the geometry of motions and the different aspects of fluid motions. What are the different aspects of fluid motions? But without finding out the cause, the motion will take place only there is a force. But kinematics does not describe the force part, only the geometry of motion. What are the different aspects of motion and consequences of motion? For example, a solid body, just a very simple thing we know, that a solid body, if it moves, all particles moves with the same velocity or same acceleration if there is a linear motion of a solid body. So particle to particle, the velocity or acceleration does not change. Similarly, if a solid body is given a rotation, so all particles in the solid body have the same angular rotation or angular acceleration. But in case of a fluid, the different particles move with the different velocity, as we have already appreciated at the beginning of this course when we discussed the viscosity. So these are the aspects which gives certain different characteristics of fluid motion like translation, deformation, rotation. This we will be recognizing in this chapter of fluid kinematics. Without going into detail, without going into any of the causes that force or anything else which will come in the fluid dynamics part. So, in kinematics, let us first then concentrate that there are two approaches which describe fluid kinematics. There are two approaches. One is the Lagrangian approach. One is the Lagrangian approach. Try to understand. One is the Lagrangian approach. Another is the Eulerian approach. There are two approaches. Eulerian approach. This will be very important even when you will read thermodynamics. This you should know. One is due to the scientist Lagrange, another is due to the scientist Euler. So, if we see what is Lagrangian approach. Now, in Lagrangian approach, let us understand first before writing the mathematics, because we will have to understand physics first. Mathematics will automatically follow. Mathematics is a tool, it will automatically follow. So, Lagrangian approach, what is done, each and every fluid particles are traced. That means in a flow field composed of several fluid particles. So, each and every fluid particle is traced and its kinematic behavior is found out, which means that if we identify a fluid particle, how a fluid particle will be identified? By giving its space coordinates at a given interval of time. For example, at time t is equal to 0 from when we start our observation. Then we try to find out its location in the flow field. So, its path in the flow field is traced with time. And this way we cover all the fluid particles that compose the flow field. This is the basic approach of the Lagrangian. That is the Lagrangian method or Lagrangian approach. So, let us now write this mathematically, that if we have a flow field, the displacement S of any particle, of any fixed identity particle, is a function of the identity of the particle, which is S0. The identity is fixed by its position vector at time t is equal to t0 and time t. That means this is in simple one line the definition of analytical expression of Lagrangian approach. That means the position vector of any identified particle is identified by its initial displacement or initial position, rather you can tell initial position from a frame of reference, and it is a function of the identity and the time. And this way all the particles of different identities are traced. For example, if we consider a x, y, z coordinate, let us consider an x, y, z coordinate, where the position vector can be written as I x, I j k are the unit vectors in I j x y and z direction. Then this we can write that x in scalar components k j, I j y, very good, plus k j. So, x is a function of the identity of the particle x0, y0, z0. That means we consider at t is equal to t0, set t0, x0, y0, z0 is the position of a particular particle. That means, so this is the identity of the particle and time t. Similarly, we can write y as a function of x0, y0, z0 and t. Similarly, we can write z as a function of, in terms of scalar component, this is the vector representation x0, y0. That means the displacement of a particle is a function of its identity and the time. Similarly, if we want to find out the velocity of a particular particle of fixed identity, it will be dx dt, and this will be some function of x0, y0, z0. These are the variables and time t. Similar is the case for dy dt. This will be some other function of the same thing, same variables. Similarly, the y component of velocity dz dt is the some function, let some function of this. Similarly, if we want to find out ax is du dt or double derivative. So, this will be a function of x, y, z0, t0. Similarly, ay, az. So, therefore, we see all the kinematic parameters, that means this displacement, velocity and acceleration of a particle is a function of their identity and the time. So, this way we can find out the description or kinematic behavior of all particles. So, this approach is very fundamental in nature. This approach is very fundamental in nature because it traces all the fluid elements that composes the flow. And one very important point of this approach is that the conservation of mass is inherent in the Lagrangian approach, in this approach, because when a fluid flows, the mass has to be conserved. So, the kinematics should be such, the kinematics of the flow should be such, it must obey the law of conservation of mass. So, conservation of mass is automatically checked because each and every individual particles are traced. So, this is one advantage, but this method is not followed or it is not convenient, it is not in use because of the most disadvantageous point that the integration of equations become very tough. Just see this, that if we are prescribed with UVW for a particular particle Ax, Y, Az, so to integrate these equations, which I will show you afterwards through a problem, sometimes the integration of this to find out the path of the particles become very difficult. So, because of these mathematical complications, this method is usually disregarded. So, therefore, the method which is in common use is the Eulerian approach, and it is the most convenient method. Now, let us see what is Eulerian approach then. Eulerian approach or Eulerian method, Eulerian method or Eulerian approach, whatever you call. In Eulerian approach, what we do, we do not trace the particles with identity. In a flow field, we just concentrate at a point. That means a field is described by the space coordinates. That means we define a frame of reference and the entire flow field is described with respect to the coordinates reference with respect to a frame of reference. That means we concentrate on fixed points which are specified by its coordinates, and then we describe velocity or acceleration at that fixed point, at all points. Fixed point means all these fixed points as a function of the space coordinate of the points and the time. In general, we can tell in a flow field, Eulerian approach writes the equation of velocity or acceleration as a function of space coordinates and the time. That means velocity will vary from point to point even at a given interval of time. At same interval of time, you will see the velocity and acceleration varies from point to point. Similarly, the velocity and acceleration may vary, these kinematic parameters, at a point with time. So, therefore, velocity and accelerations are expressed as function of space coordinates and time. So, if you clump the Lagrangian and Eulerian approach, you describe the Eulerian approach, a flow field is described by Eulerian approach. Then the kinematic Lagrangian approach, a fluid particle is traced. So, the velocity and acceleration of a fluid particle at any instant will be the velocity and acceleration of the point at which the fluid particle exists at that instant. So, a fluid particle passes through different points at different instant. So, the instantaneous values of the velocities and acceleration at the point where it crosses is the velocity and acceleration that the particle assumes. There is the physical link between Eulerian and Lagrangian approach. Let us write the Eulerian approach then in mathematics. So, Eulerian approach in mathematics writes the position, not the position vector, the velocity vector is a function of, velocity vector is a function of space coordinates and time. Similar is the acceleration vector is a function of space coordinates and time. That means, if you consider a frame of reference, simple rectangular Cartesian coordinates, this is y, this is x in proper sense of rotation. Then with x, y, z, if a flow field is described with the coordinate x, y, z at any point, then we can write the x component of velocity is a function of x, y, z. So, we can break this vector form into scalar components is a function of x, y, z. That means, this x, y, z is not the coordinate of a particle, it is the coordinate of a point. So, w is a function of x, y, z and t. Similar is the case for acceleration. Ax is a function of x, y, z and t. Similarly, ay is a function of x, y, z and t. and similarly Az is a function of. That means here the velocities and accelerations are described as a continuous function of space coordinates and time, and this is permissible in the continuum mechanics with the continuum approach. Assumption for a continuum, as you know, any property can be described as a continuous function of the space variables and time, and this is done for Eulerian approach to represent the velocity components or the velocity vector in one vector equation and the acceleration vector as a function of space coordinates and time. So, this is the Eulerian approach. So, therefore, Lagrangian approach tells that when a particle comes at a particular point at a particular time, so the velocity vector at that point at that time is the velocity of the particle which comes at that point. Next, we will come to the concept of uniform flow and steady flow. Uniform flow and what is uniform flow? What is steady flow? Now, what is steady flow? First we start what is steady flow, this one. A steady flow is defined where all hydrodynamic parameters, all, not the kinematic parameters only, are invariant with time. There is no change with the time. The parameter may have a distribution over the space coordinates. That means there may be a variation of the parameters over the space coordinates. Let us discuss in terms of velocities only, because we are discussing kinematics only. Velocities and accelerations are changing with space coordinates. So, we have a variation. In a 3-dimensional plane, we can consider the plane of variation. In a 2-dimensional plane, we can consider a variation by a single curve. That means there is a variation, there is a map of the velocities and acceleration, but this map or these variations over these space coordinates remains invariant with time. That means in a simple way we say that if we fix a particular point, fixed point, then the hydrodynamic parameters, all hydrodynamic parameters remain same invariant with time. That means this is known as steady flow. So, therefore, in a steady flow, the Eulerian approach say that V bar is not a function of time. That means the only consequence is that V bar is a function of S, space coordinate only. Sorry, this is a functional notation, I am sorry. Similarly, the acceleration is a function of space coordinates only. That means the hydrodynamic parameters and all other parameters cease to be a function of time. This is known as steady flow. On the other hand, what is a uniform flow? Please tell me what is a uniform flow. You know that thing, when the velocity and acceleration is not a function of space coordinates. Very good. That means V is a function of time only. Similarly, the acceleration is a function of time only. This ceases to be a function of space coordinates, uniform flow. That means the velocity and accelerations are same throughout the space. Now, in general, a fluid will be both non-uniform and unsteady. So, unsteady flow is a flow where the hydrodynamic parameters along with the kinematic parameters are functions of time. Similarly, a non-uniform flow is a flow where the hydrokinematic parameters are a function of space coordinates. So, different possibilities may appear. Most simple case is uniform and steady flow. Flow is uniform and steady. So, nothing to be done, no solution is required in this case. So, that means the velocity vector, for example, or acceleration vector does vary neither with space nor with time. That means in this case velocity vector is throughout constant, is a constant. Now, in case of another uniform unsteady flow, another case is these are very simple, uniform unsteady flow. Okay. So, in terms of V, we can tell uniform flow. So, it is not a function of space coordinates because of the unsteadiness, it is a function of time only. Another thing may come, that is uniform unsteady. So, non-uniform steady, non-uniform and steady. In this case, what will happen? It will be a function of S only, because it is the steady flow, it is the function of S only. And most general is non-uniform non-uniform and unsteady, and unsteady, where V is a function of both S and T, general nomenclature, it is a function of S and T. In engineering applications, flows are never uniform, uniformity is never there, always, because uniform flow is available only in solid body motion. Usually in a fluid, this is by virtue of the property of the fluid, because of its viscosity, flow is always ununiform or non-uniform, but in some cases we assume the flow to be non-uniform. But regarding its steady and unsteady situations, many engineering applications pertain to steady flow, but many engineering situations pertain to unsteady flow. It is very clear that steady flow poses more simplifications, rather unsteady flow poses more complications, because the function time comes into it. So therefore, if a flow is steady, it becomes more simple. If a flow is uniform, it is the simplest one, which is not the case in practice. So therefore, unsteady flow problems becomes complicated in practice, whereas steady flow problems are simple. This is the reason for which sometimes we choose axis properly to make many unsteady flow problem to become steady. So a problem, whether it is steady or unsteady, problem may be in absolute scale unsteady, but sometimes if you choose the frame of reference against which the analysis is made, some flow may become steady. I can give you one very simple example which I have given in my book, if you have read that if you just go with a boat or a ship or with a launch through a river, you will see that while you are sitting on the boat, any point on the river, boat is moving and you fix any point in the neighborhood of the boat or anywhere in the river, you will see the flow condition is steady. That means the total flow field which is being generated, or we can see, always you see a similar type of flow of water surrounding the boat. Or if you fix your eyes to a large distance at far away stagnant water, for example, there also you see always as you move with the boat, the far away point is always at rest. So this far away point with respect to you. Now what happens? You are moving with the boat, that means you are observing it, the coordinate axes are fixed to the boat. So with respect to the boat, the flow field is steady. But if you consider an observer who is at absolute rest, that means an observer standing on the bridge or an observer standing on the shore of the river, if he concentrates at a particular point with an Eulerian approach and tries to find out the flow field, he will see the flow field is changing with time. For example, a person standing on the bridge, what if he just looks at the bottom, at a point at the bottom of the bridge in the river, he will see that when the boat is far away, this point is at rest, V is equal to 0. As the boat is approaching, some flow field is being generated and it is getting changed. It acquires some flow velocity which is very high when the boat is very close, and when it goes away, the flow velocity is again dying out. So this way, if he sees at any point, he will find out an unsteady flow field, whereas a person moving with the boat, if he concentrates at any point in the river, he will find out the flow field is same with time. That means a steady flow. This is a very good common example where you can appreciate afterwards when you will be studying the control volumes, the reference to a particular frame of axis, the unsteady flow may be made steady for simplification in analysis. All right. Now let us come to the definition of acceleration. Now I will ask you one simple question. Since we are acquainted with this term acceleration, velocity since our childhood, you can say, from class 8 or class 9 level, whenever we have come across physics, physical science. Now what is the definition of acceleration? Please tell me, what is the definition of acceleration? It is the rate of change of velocity with time. Now can you tell when the flow is steady, acceleration is 0? Yes. Okay, yes. Let us now see, though it is wrong, but I tell you, because I know that it is difficult for you to tell yes. For example, if a fluid flows through a convergent duct nozzle, as you know that a fluid flows through a convergent duct, at the inlet where the diameter is more, fluid velocity is less. This will come afterwards from the continuity, but as at least I know at this stage you can appreciate this. When it flows through the converging nozzle and comes out from the small discharge area, then the fluid acquires a very high velocity. So therefore, fluid enters with a very low velocity and acquires a high velocity. Now under steady conditions, as far as the definition of steady flow, I can tell that the fluid velocity varies from point to point. That means if you consider at the time being the flow is not varying in this direction and cross section, only varying in the direction of flow, one dimensional, then I can tell at the inlet the velocity is low, at the outlet velocity is high. But whatever may be this velocity variation, it remains invariant with the time. That means the velocity of flow at the inlet is constant with time. Velocity at any sections in the nozzle is invariant with time, and the velocity of discharge is also invariant with time. That is, the liquid is coming with the same velocity out of the nozzle. So in this case the flow is steady or not? Steady or not? Steady. But is there an acceleration of the liquid? Liquid is accelerated from a lower velocity to a higher velocity. So why do you tell then if the flow is steady, the liquid will not be accelerated? Now you see, a liquid particle accelerated not because the velocity field changes with time, but because of its convection. Why in this case we call the fluid particle is accelerated if we consider a fluid particle? Now we come to the Lagrangian approach. As it flows from inlet to outlet, it suffers a change in velocity. That is why it has an acceleration. It is a positive or negative depending upon the shape. As you know that if there is a diverging passage, the fluid will be decelerated. It is a change in velocity it suffers because of a spatial variation of the velocity. So when things are flowing, its acceleration is because of its convection, and this acceleration is due to a gradient in the space, that means because of a change in the velocity in the space coordinates, and at the same time the change in the velocity with respect to time. I have given you an example, a steady flow but non-uniform flow. Now if the flow becomes unsteady, that means if in this case practically if I vary the flow rate at the inlet, that means the flow at the outlet will be varying, and as a whole in the converging duct the variation of velocity will vary from instant to instant. So in that case what will happen, a liquid or fluid particle at inlet has got some velocity which is the velocity at the inlet at that instant. When it is convected to the outlet, it will have an acceleration. Why? This is because its velocity that it will assume, that is the velocity existing at the outlet at that time, because this takes care of both the change in the velocity due to space coordinates and the change in the velocity due to time. So therefore these two things are responsible to make a change in velocity of any particle which is convected in a field. So therefore acceleration comes from these two causes. Both the cases, that non-uniformity of the flow field, that is the change of velocity with the space coordinates, and also with the unsteadiness of the flow field or unsteady part of the flow field, that is the change of velocity with the time. Both together determine the acceleration. So we can tell conclusively the acceleration is 0 when velocity is neither a function of space coordinates nor a function of time. That means velocity in all points are same, invariant with the space coordinates and also with time. So if there is a convection of a fluid particles, it moves from one point to other point, it will have the same velocity. So for same velocity, that means the flow is, when the flow is uniform and steady, acceleration is 0. You have understood? Even another case I am telling that if the flow is uniform but unsteady, that means there is no change in the velocity along the direction of the flow. But at any instant, this constant flow at all points goes on changing. There is also an acceleration. So space-wise, when the fluid particle flows from one point to other point, it changes its velocity because it takes time to change across. It takes time to come to a point from one point. So during that time, the velocity changes. So therefore, we see that the acceleration of a fluid particle is because of the variation of the velocity with time and space coordinates both. Have understood this? Okay. So this is most important point in the fluid flow, that is the acceleration. Now let us derive an expression for this acceleration component. Now, well, let us consider in a Cartesian coordinate system, the velocity of a point is given by u, v, w, three components, u, v, w. And let a particle is at a point whose displacement and the position vector is fixed with respect to this frame of reference. Now, let us find out after a small time interval delta t, the change in the velocity component, the particle has gone here for example from A to B. The change in the velocity components is delta u, in v delta v, and in w component delta w. Then we can write that now u v w we can write from Lagrangian approaches. U is a function, Eulerian approaches, x, y, z and t. With the Eulerian approaches, we can write x, y, z and t. We can write this simple mathematics that at any point the velocities can be written like this. Now the increment in velocities in any one of the components with delta u, with that we can write the u plus delta u, that means the change final u component velocity after a time delta t when the particle is displaced from A to B can be written as u as a function of x, y, z, t, and with the Taylor series expansion we can write del u, because u is a function of x, y, z. So a change in u is caused by a change in x, y and z and t simultaneously. These are the independent variables defining this function. Del u del x plus, this is simple Taylor series expansion. That means a dependent function is a function of its independent variables, and a change of this function due to the change of the independent variables simultaneously plus del u del z. These u are functions of x, y, z times del z plus, well, del u del t del t. Now here we assume that during this time interval delta t, when the particle has moved from A to B, it has got a x coordinate change by del x, y coordinate change by del y, z coordinate change by del z, del x. That means the position vector is s, here the position vector is s plus ds. Understand? So s is I x plus j, I, j, k are the unit vectors along x, y and z axis, y plus k z. Similarly, the displacement vector ds is I del x plus j del y plus k del z. That means del x, del y, del z are the displacement during delta t time. Now this u cancels. So one can write del u and dividing it by delta t, del u delta t, and taking this term first, del u del t plus del u del x del t plus del u del y del t plus del u del z, you can see del z del t. Okay. So I can write this, del u del t is del u del t plus del u del x, just dividing by delta t, del x del t plus del u del y del t plus del u del z del z del t. Now if I take a limit of this as delta t tends to 0, delta t tends to 0, then we can write this is simply del u del t plus, because at delta t tends to 0, delta u will tends to 0, this will be a finite one and delta u delta t. This is invariant with that, so this limit we can write del u del x into limit of del x del t, this quantity, as del t tends to 0 plus del u del y limit of this quantity del y del t as del t tends to 0 plus del u del z limit of del z del t. Now you see these quantities, limit of del x del t, del y del t, del z del t at del t tends to 0, both del x tends to 0, del t tends to 0, del y, but this retains a finite value, and by definition this is the x component of velocity at a point. That means the x displacement divided by the time and limiting value as time tends to 0. That means it quizzes to a particular point when del t tends to 0, del x tends to 0. So by definition from preliminary mechanics, this is the x component velocity, this is the y component velocity. That means this is u, this is the y component velocity v, and this is the z component of velocity w. So therefore we can write now this as, now this del u del t at t tends to 0 can be written as du dt. Big D usually is written. It becomes is equal to del u del t plus, if I write u del u del x plus v del u del y plus w del u del z. In a similar fashion, if we expand the v component, we can write dv dt is equal to del v del t plus u del v del x. You do it, you will see in the similar fashion we can find out v del v del y. Now here I have forgotten to tell you one thing, I am sorry, that when I expressed it, please go back to the earlier slide. Here there were terms, this is higher order terms, because you can ask me, sir, why you have not written this in Taylor series. Higher order terms in del x, del y, del z, del t. That means this is the first order term, as you know, then the term will come of the higher order of this, where delta x square, delta y square, delta t square will be there. So therefore, when you divided it by delta t, these terms of order delta t and more. So therefore, when you divided it by delta t, so you will see the higher order terms will be there. So automatically when you will take the limit, this term will be cancelled, because this term will automatically become 0. When you take the limit of this as delta t tends to 0, the higher order terms in delta x, delta y, delta z, delta t will automatically go down to 0. Obviously, it will go down to 0. Here this first order term will not go down to 0. Any term delta x whole square by delta t, limit will be 0 as delta t tends to 0. Similarly, any term containing delta t in the numerator as a net product or delta t square, the limit will be 0. This simple mathematics you can see that the higher order terms in delta x, delta y, delta z, where it comes here in the term square, then cube. So higher order terms if we take, then after dividing by delta t, the terms which is left, which will be yielding 0 values when you take the limit of this as delta t tends to 0. So therefore, we have take this as 0. So all the terms are 0. Now we come here u and v, and similarly we can write that dw dt, if we expand w component, we will get del w del t plus u del w del x plus v del w del y plus w del w del z. So these are the three. So this is the acceleration in x direction, that is ax. This is the acceleration in y direction, that is ay. This is the acceleration in the z direction. So therefore we see, for example, in one component, the x direction acceleration is composed of one term which is responsible for the change in x component of velocity with time, and other three terms are connected with the space derivatives, that is the term responsible for the space wise variation of x, y, z. Now if the flow is steady, that means u, v, w are not the functions of t, then the first term is always 0 for the acceleration. But still acceleration is there because of this component, that is this space wise derivatives. If the flow is uniform, then these three terms in the right hand side in the expression of accelerations are all 0. So only the first term exists. So therefore we see this is the situation. Okay, thank you.